Okay, we're on. There's another exciting definition for you. The enthalpy change when 1 mole of bonds of the same type are broken in gaseous molecules under standard conditions averaged for different compounds. Do like to come out with our lengthy, wordy definitions in chemistry, don't we? Enthalpy change when 1 mole, well, enthalpy of formation and enthalpy of combustion both started like that, so that's a common beginning. But now we are breaking bonds. You might remember that for mean bond enthalpy, right? That you're breaking bonds. That's probably not the hard bit. In the gaseous state, we're talking about gaseous molecules only. That might slip away. Understanding the conditions is just slipped in there. But then averaged for different compounds. Okay. Each bond has its own bond energy or bond enthalpy. I'm going to use bond energy and bond enthalpy interchangeably because it used to be called bond energy, you know, when I was a lad. Yeah, because I was doing this when I was 6, obviously. And yeah, we're going to use it for calculations. No different from GCSE. In fact, if you look at the GCSE problems that AQA have served up in their exams, you can see they actually just copied them from A-level papers because things trickle down, right? Stuff that 10 years ago we didn't teach in GCSE, like mean bond enthalpy, have now arrived there. Yeah, there's quite a lot of stuff we teach in GCSE now that you had to do that people did 10 years ago didn't. Exams generally get harder. Anybody who says in any newspaper, oh, exams are really easy today, it's just talking nonsense. It's because they've not been a teacher for the last 30 years and they haven't seen how things have actually got harder slowly. It's just that students have got better at learning. That is true. Anyway, I digress. That's just, you know, speaking as an internet influencer, I felt the need to get that out there. Okay, so bond enthalpies are all different for different bonds, and we can get a table of data, and we'll get to that in a moment. All right, so if we've got a reaction equation like this, we can kind of break it down bond by bond and look at the energy that goes into breaking all the bonds and the energy that we get back from making all the bonds, and then we can come up with a difference. Now, I find it very useful to write out the so-called displayed formula. Displayed formula show every bond in a molecule. So could you, for methane reacting with oxygen, draw me some displayed formula of these things? I'll start you off. The displayed formula for methane would just look like that. Right, can you just draw me the displayed formula for those things, please? So the key thing here is that you remember the difference between single and double bonds, and often a lot of mistakes rest on that confusion. In fact, having just marked the year 13 mock exams, I can tell you that that confusion was still there in year 13. So yeah, oxygen bonds are of course double bonds because oxygen always has 2 bonds and carbon always has 4. So we've got double bonds there. Don't forget honk 1, 2, 3, 4 if you've forgotten the number of bonds. And water looks like that. And if you really want, you can remind yourself of the shape of the molecules. Of course, carbon dioxide is linear and water is angular or bent. Okay, so having done that, we can now get a table of bond energy data to work that out. So I would be fairly thorough about this because, again, this is often an area where people just miss something, and it, you know, with lots of bonds, with bigger molecules, lots of numbers on the page, it's really important to keep it clear. I might show you a page from someone's year 13 paper. Oh no, I can't because Miss Evans is marking them. Okay, never mind. Maybe another time, with his permission, obviously. Okay, so we have some mean bond enthalpy data there. Just to clarify, the CH mean bond enthalpy is the reaction for turning a carbon-hydrogen thing attached together in the gas phase into a free carbon and a free hydrogen. That's what we mean by bond enthalpy. We're breaking that bond, but it has to be in a gaseous state. Could you do it for me? Thanks. Just do it. Work out the enthalpy change for that reaction. Let's just see. Okay. Anybody got an answer? Just before we jump to the answer, what kind of answer are you looking for? A negative number. How do you know it's negative? Because it's combustion. Okay, so you're familiar with this type of diagram, an energy profile diagram. So what I need to do to complete the rest of this diagram? Could somebody sort of draw it in the air for us? Thank you. Okay, so it has to look like that. Because it's an exothermic reaction, so we've lost energy here. On this diagram, what are we doing on the way up here? What's happening to the methane and the oxygen on the way up this bump? What's going on?
They're gaining energy.
To do what? What's the energy? What work is the energy doing?
Oh, breaking the bonds.
Right. Okay. So we're breaking bonds. So we might imagine at the top here we've got a whole bunch of things. Got a whole bunch of atoms, all independent, and they're all kind of just flying around freely. And then going down this way, we are forming bonds. Okay. And of course, going up, that process of increasing the energy of the atoms, the particles, means they're gaining energy, means that bit is endothermic. But on the way down, that bit is exothermic. So breaking bonds requires energy, always. It's a good chemical principle to have really well fixed in your mind. If I ever want to pull two particles apart, I have to put energy in because they're glued together with these amazingly strong covalent bonds. What's less obvious is that when I put them back together, I get energy back, which doesn't happen when we glue two things together. We don't suddenly get a burst of energy, feel all kind of warm and fuzzy inside. But that's what happens for atoms. When we put them together, we get as much energy back as was needed to break them apart in the first place. Because, of course, if it's delta H positive in that direction, then it's delta H negative in that direction for the same amount of energy. So, did we get an answer? Somebody want to go for it?
Negative 684.
684 we're getting. I get 678. It's alright, it's on YouTube, don't worry about it. On the left we've broken some bonds, so 4 lots of CH, 2 lots of oxygen, I get a total of 2660. 2 lots of CO double bonds, 4 OHs. Don't forget it's 4 because we've got 2 waters, so 2 waters is 4 OH bonds, 33, 38. And then my bonds on the left are all endothermic, so positive. My bonds on the right are exothermic, so negative. So these minus these gives us my overall negative value. You found where it went wrong?
I'm trying to.
Is it just?
Oh, copy something down.
Yeah. It's like I said, it's a very common area for students to make just sort of careless numeric mistakes because there's just so many numbers, so much data. None of this is very difficult. You just, you know, multiplying numbers and adding them together and subtracting, but again, it's so easy to lose track of what you're doing. You need to be really careful and methodical. All right, let's do another quick one, and then we'll do a bit of GCSE. Calculate the energy change when hydrogen gas burns. What value are we looking for here, approximately?
Negatives.
Minus 286. Yes, you just had it, didn't you? So there you are. You know, you've got that value shouldn't be far off. We'll talk about why it might be not exact in a minute. Okay, it's really nice to have a conversation at the back there with some people at the back saying, you know, that can't be right. No, I just don't want to name you live on YouTube, Charlie. It's all right. Okay. No, it was a good conversation. That a bit of doubt is really good. If you can engineer that, if you can look at your value and go, is that right? Is that reasonable? That's really, really useful. That just to create that habit, that sense of doubt. In the same way, you know, if you watch something on on TikTok or whatever it is, you kind of go, is that real? They just faked that. They just made that up. You know, that to have the same sense of doubt over your own data is really useful because we make mistakes all the time. It's really common. Okay, I'm not going to do that one. Or am I? I thought I had a better one. There we go, that's better. Type of fuel cell used is methanol. The equation represents the reaction in this fuel cell. Table of bond energies, blah, blah, blah. Overall enthalpy change. Do it. Yeah, so again, try and keep your work tidy. It helps to have a displayed formula drawn, but obviously at A level you will need to do that. And you know, really keep these balancing numbers clear in your mind. Maybe make them large and red or something. So we've got 6 lots of carbon-hydrogen bonds and 2 carbon-oxygen bonds, 2 OH bonds, and then 3 lots of oxygen-oxygen bond. And it's good to total both of the sides as well. So bonds broken, 5, 6, 1, 4. There'll be a mark for that. Bonds formed, 4 lots of CO double bonds, and 8 lots of OH bonds. 6, 9, 3, 2. Again, there'll be a mark for that as well. And then the final mark is for doing bonds broken minus bonds formed. Minus 13, 18. So try and keep your work tidy. And again, if you write down all the numbers before you hit a calculator, that makes it much easier for you to check. But that all important 10 minutes at the end of the exam when you've done everything, you haven't got anything else to do, you know, you're fairly sure that most of your answers are right, you just go back and check your maths. That's all you need to do there. Okay.